Hi guys, and welcome to this video where we're going to be going through a specimen paper for AQA GCSE Physics. This is the specimen 2018 paper. This is the higher tier paper, and essentially in this video we're going to be going through the whole paper from start to finish under exam conditions. So let's get straight into it. Okay, so question 1. Figure 1 shows a balloon filled with helium gas. Describe the movement of the particles of helium gas inside a balloon. Now, for this question, what we need to consider is what are the qualities of gaseous particles in the gaseous form. And so for that, we're essentially looking at the fact that these particles are going to have a range of different speeds. So we're going to have all sorts of speeds going on with these particles. And so some particles will be moving faster than others, and some will be moving slower. And the idea behind that is essentially that out of the three states, your solid, liquid, and your gas, your gaseous particles are going to be the ones with the least order and can have the most kind of free form movement. And so part of that also is the fact that they are also going to be moving in different directions. So it's the same kind of thing that you have random directions and random speeds essentially. So our direction is also going to be completely random. So you can write that down. And for 2 marks, we're going to put our 2 points. So those would be our 2 points. For the next question then, what name is given to the total kinetic energy and potential energy of all the particles of helium gas in the balloon? And so this one is a multiple choice question. We've got options of external energy, internal energy, and movement energy. And so the kinetic and potential energy within a substance is called the internal energy. So you've got to tick that box. Question 1.3, write down the equation which links density, mass, and volume. And so you should know that density is equal to mass over volume. So essentially density is the mass per unit volume. You can think of it like that. And our next question basically plays into the units. So for our next question, we have the helium in the balloon has a mass of 0.00254 kilograms, and the balloon has a volume of 0.0141 meters cubed. So two numbers there. Calculate the density of helium and choose a correct unit from the box. And so there's two parts to this question. Essentially, first we do our calculation, and then we need to work out the units. So let's do the calculation first. And so the formula is given to us at the top here. So we've already done that in the previous part. So the density equals the mass over volume. So mass is 0.00254 kilograms. And you just got to divide that by your volume, which is 0.0141 meters cubed. And if you put that into your calculator, you should get 0.18 if you round that off to 0.18. And so our answer is going to be 0.18. And for the units, it's going to be your kilograms per meters cubed. So you can write that in like that. And so out of the options here, you could kind of have to think about what you're doing. And so in this case, our mass here is given in kilograms, and our volume is given in meters cubed. And so when we do this calculation, you think about what we're doing the kilograms divided by the meters cubed. So essentially it's the kilograms per meters cubed, and that's how you get your units. Okay, and that's it for question 1. Okay, question 2 then. Scientists sometimes replace one scientific model with a different model. For example, in the early 20th century, the plum pudding model of the atom was replaced by the nuclear model of the atom. Explain what led to the plum pudding model of the atom being replaced by the nuclear model of the atom. Okay, so here we've got a 6-mark question. So in this case, we've got to think about how do we approach 6 markers. Well, 6 markers, essentially you can a lot of the time what you can think of it is you're going to split it into 3 different points which are all going to be linked together, and each point is going to be worth essentially 2 marks. And so depending on the question, that model can work. Sometimes you might want to split it into 2 different points where we think it was 3 marks. And to show you what I mean, let's go through this one. And so essentially we need to think about we have the plum pudding model and the nuclear model, and our question is asking us essentially what led to the plum pudding model of the atom being replaced by the nuclear model of the atom. So what you can start off doing essentially is describing what is the plum pudding model. So the plum pudding model, you can say, what is the key features of the plum pudding model? And essentially, for the plum pudding model, you have a ball of positive charge with essentially negative charge embedded into it. And so I'm going to write this shorthand, but you guys can obviously write this all out in more detail. So negative charge is going to be embedded into it. And essentially, what was the experiment then? If we're going to answer this question directly, what actually led to this being replaced? What was wrong with the plump-pudding model, and what was the process in getting this replaced with a nuclear model? Well, you should know from your revision that this was as a result of the alpha scattering experiment. So the alpha scattering experiment, and what actually happened in the alpha scattering experiment? Well, let's describe what happened. So essentially, we had alpha particles directed at a sheet of gold foil. And then what were the observations once we shot the alpha particles at the gold foil? Well, most of them went straight through the gold foil. And so what was the conclusion? If most of them went through straight through the gold foil, what can we conclude? Well, we can conclude that most of the atom was empty space. Empty space. Okay, and what was our second observation? Well, in the alpha scattering experiment, there was two observations, and the second one was essentially that some of the alpha particles were deflected at large angles. So some alpha particles deflected at large angles. Okay, so what does that tell us? Well, essentially, if some of the alpha particles deflect at large angles, that tells us that the most of the mass is going to be concentrated at the center of the atom. So why were they deflected? Well, we have a positive mass concentrated in the middle, in the center of the atom. Okay, so how do we know it's a positive mass? Well, essentially, what would cause the alpha particles to be deflected? Well, it's the fact that you would have some electrostatic force between the alpha particles and some kind of positive mass. And where was that? Where did that occur? Well, it occurred at the center because most of the alpha particles passed straight through, and only some of them interacted with this positive charge. And so that tells us that we've got a small, dense positive mass at the center of our atom. Okay, so essentially then we can outline now our new model, the nuclear model. So according to this then we can say that the nuclear model basically helped us develop a model that agreed with those observations, because these observations didn't agree with the plum pudding model, because the plum pudding model, essentially, as we've kind of mentioned here, we had a big ball of positive charge with negative charge embedded into it. So when we have the alpha scattering experiment, we wouldn't expect the alpha particles mostly to go straight through, and we wouldn't expect only a small proportion of them to be deflected. And so that comes to our nuclear model. And so essentially we can say that in the plum pudding model, the mass was kind of spread out. The mass was kind of spread out throughout the atom, which disagreed with our thing. So a nuclear model, we have the kind of dense positive concentration of mass in the middle. And the other point you can mention is about the charge. So same thing with the charge essentially, and we've kind of mentioned it in that. And so that should be enough for your 6 marks. So what we're discussing in terms of the way we're going to split our answer up is that you've got three different sections here. So in the first section, we're kind of identifying what the plum pudding model is. This is not directly answering the question, because the question is essentially is this bit here. So we need to consider that. And so part of that then, the main section is going to be the alpha scattering experiment. So you're going to describe what essentially happened in the alpha scattering experiment. So that would probably be worth a mark. And then your observations and your conclusions are probably going to be worth about 4 marks. And then a nice kind of concluding bit here going to be worth the 6th mark there, if that makes sense. Okay, so that's it for question 2. Okay, question 3 then. The national grid ensures that the supply of electricity always meets the demand of the consumers. Figure 2 shows how the output from fossil fuel power stations in the UK varied over a 24-hour period. So 3.1 suggests one reason for the shape of the graph between 3 o'clock and 6 o'clock on Monday. So if we've got 3 o'clock is going to be about there, and 6 o'clock going to be about there, around about this peak here. And so essentially it's asking us to explain why the graph basically increased between these times. And so you've got to kind of this is a suggest question, so it's not kind of set in stone. You won't be taught this directly, but you should be able to make a reasonable suggestion about why this would happen. So you go think about between 3 o'clock and 6 o'clock, what major event might happen which would cause our total power output to have to increase. And so something a simple suggestion would be something like um, people come back from work or school, and when you come back from school, um, you might have higher energy demands. And the reason for that is essentially that you might come home and you put the TV on, you put the kettle on, or whatever. And so you can imagine that if everyone comes home at the same time, you'd have a larger demand for energy at that kind of moment. Okay, 3.2. Gas-fired power stations reduce the output when demand for electricity is low. Suggest one time on figure 2 when the demand for electricity was low. So again, it's just a pretty simple question here. I'm going to look at when the demand for electricity was low. Well, they're kind of giving you the answer here that the output is going to be low. The output is going to be reduced when the demand is low. So whenever the output is low, the demand will be low. And so we just go to a low point in the output. Let's take this time at random, about 2 a.m. let's say, and that should give you the answer. So you can say about 2 a.m. 2 a.m. on Tuesday, and that should be fine. Okay. 3.3. The national grid ensures that fossil fuel power stations in the UK only produce about 33% of total electricity they could produce when operating at maximum output. Suggest 2 reasons why. So what this question is asking us essentially, um, when we have the national grid going, we only want to produce 33% of the total electricity from the fossil fuel power stations of their total capacity. So if you imagine if you had them at maximum output, we produce 100% of our electricity, but instead of that, we only want to produce 33% at any one time. So why? What would be the reason behind that? Why would we not want to operate them at 100% capacity and have that as kind of the design? Well, there's a few different answers here. Again, it's a suggest question, so you've kind of there's a range of different answers that you can select here, and as long as they kind of make sense, you'll be able to get the mark. So a few things I can think of. Essentially, you want to conserve the fuel. So this basically allows us to maintain basically stores of fuel, if you imagine, and it ensures that we have some kind of capacity, some kind of spare capacity in the network. So the way that the national grid works is that when the demand increases, we increase the output. But in some cases, we may not be able to perfectly predict the demand. It might be higher than we expected. So if you imagine if we're only operating at 33%, if there's extra demand, we can easily increase our capacity by a few percentage points to meet that extra demand. And if we operate at 100% capacity, then essentially we wouldn't be able to do that. And so having that extra built-in capacity allows us to kind of have this room for error. Some other things basically, also, if you imagine all of this energy is coming from fossil fuels, if they're fossil fuel power stations. So if we only need 33% of total electricity to power it, there's no reason to have our power stations running 100% capacity. We're just wasting fuel, and we're also emitting harmful greenhouse gases, which we don't need to do, and that would make a bad environmental impact. So hopefully that makes sense. So that's it for question 3. Okay, question 4. A student investigated how much energy from the sun was incident on the Earth's surface at her location. She put an insulated pan of water in direct sunlight and measured the time it took for the temperature of the water to increase by 0.5 degrees, 0.6 degrees Celsius. Sorry. The apparatus she used is shown in figure 3, and choose the most appropriate resolution for the thermometer used by the student. So we've got a few different options here of 0.1, 0.5, and 1 degree Celsius, and we've got to choose which one would be the most the best resolution. So the way we do this, we want to look at essentially what is the student measuring. Well, she's measuring the time it took for the temperature of the water to increase by 0.6 degrees Celsius. So she needs to be able to read a measurement of an increase of 0.6 degrees Celsius. If you imagine the temperature started at 1 degree Celsius, if you want to then read it to 1.6 degrees Celsius, well, if the resolution was only 1 degree Celsius, then we wouldn't be able to tell until this went to 2. So we'd have basically, we wouldn't really be able to tell when it's 1.6, we just have 1 and 2. if the resolution was 0.5, then we'd go 1 to 1.5 to 2. So again, you'd have this room for error. You wouldn't be able to get 1.6 exactly. And so we can see that we need 0.1 degrees Celsius in order to perfectly measure 0.6, an increase of 0.6. And so 0.1 would be our answer here. So I'll just put that in black. So next, the energy transfer to the water was 1050 joules. The time taken for the water temperature to increase by 0.6 degrees Celsius was 5 minutes, and the specific heat capacity of water is 4200 joules per kilogram degrees Celsius. Write down the equation which links energy transferred, power, and time. So you should be able to know this equation. So see equation between energy, power, and time, and essentially power is just a measure of energy or energy transferred per unit time. So power equals energy transferred divided by time, essentially. Calculate the mean power supplied by the sun to the water in the pan. So we're going to take our equation from 4.2 and apply it in 4.3. And so we just need to simple substitution of the numbers given in the question. So we've got 1050 joules of energy transferred. And how long did it take? Well, it took 5 minutes. And so we should be able to get 1050. And here we need to be a little bit careful when we do our division. And so the time, you can't just put it in as 5 minutes. We need to work out that in seconds because the units in this equation should be seconds. And so 5 minutes in seconds is 300 seconds. And so 1050 divided by 300, and you should get 3.5 watts. So again, the unit in this case is given to you, and it is watts. Okay, calculate the mass of water the student used in her investigation using the correct equation from the physics equation sheet. And so for this question, you need the equation from the data sheet. And so the equation should be that the energy is equal to mc theta t. And so it might vary depending on what equation sheet you're using. But theta t might be written as delta t or something like that, something similar. But essentially, you should be able to know what this equation means anyway. So E is the energy, m is your mass, c is your specific heat capacity, and theta t or delta t is your change in temperature. And so from here, you can rearrange it and then just plug it in. So m here should equal c delta t over E. So I'm going to use delta t for this question. I just make some space here. And so then if you just plug in your numbers, and so E, sorry, so that should be the other way around. So you just need to make sure you rearrange that correctly. So E over C delta T. Okay, and then you can just plug in your numbers. So your energy was 1050, so that's from the question here. Your specific heat capacity is also given in the question. It's 4200 joules per kilogram degree Celsius. So you can put that in, 4200. And your delta T, that's your change in temperature. So what was the change in temperature? Well, it was 0.6 degrees Celsius. So multiply that by 0.6. And if you plug all of that in, you should get a mass of 0.417 kilograms. Okay. So question 4.5 then, the student's results can only be used as an estimate of the mean power at her location and give one reason why. So essentially in this question, all of the calculations we did were essentially an estimate of the mean power or the mean so in this 4.2 we worked out the mean power, if you like. And so the question is, why is it only the mean power? Why can't we say this is the actual power throughout the time period? Why is it the case that it's only the average or the mean power? And so you got to kind of think about what's going on experimentally here. And so the main thing I would say essentially is that we're measuring this over a time period of 5 minutes. Now in that time period of 5 minutes, the power could actually change. So here we've got incident solar radiation. You've got to think about over 5 minutes, the sun could start off here and it could move slightly. So obviously we're kind of exaggerating it a bit. It wouldn't move this much, but if you can imagine, the sun is moving direction, and so the angle of your incident solar radiation is also going to change. And if that changes, that could change the kind of intensity of solar radiation that's been incident upon your container here, and that would essentially change the mean power from the sun. So over the 5 minutes, the power could actually change, and because of that, we would say that this is only a mean reading of the power at that point. So that's the point I would say. That essentially the intensity of the solar radiation may change with time. So you can say the intensity or the angle uh, of the solar radiation would change with time. Another thing that could affect the intensity is also maybe a cloud passes in front of it. If you've got a cloud passing in front of your sun, maybe from minutes 3 to 4, and then there's no clouds on the other throughout the other rest of the time, then again you'd get a changing power that's been incident there at your location, and that's the reason why we can only say it's the mean power. We can only say it's an estimate of the mean power. It might not be the actual mean power. Okay. Okay, so let's move on to question 5. A student investigated the efficiency of a motor using the equipment in figure 4. So we've got a pulley wrapped around a motor, and we've got some weight at the bottom, and it's giving us some numbers here to work with as well. He used the motor to lift a weight of 2.5 newtons, a height of 2 meters. He measured the speed at which the weight was lifted and calculated the efficiency of the energy transfer. He repeated the experiment to gain 2 sets of data. So 5.1, give one variable that the student controlled in his investigation. So we're looking for a control variable here. So there's a few different ones you could pick out. And so the one that kind of jumps out to me is 2 meters here. It seems that he's lifting the weight through the 2 meters, and that 2 meters is staying the same throughout the investigation. So that would be a control variable. So the height lifted. So remember, the control variable is one that you basically keep the same throughout your investigation. Give 2 reasons for taking repeat readings in an investigation. So this is kind of a general question. Why would you bother to take repeats? And so again, there's a few different things you could say here. And so the first one I'll say to be able to spot anomalies. So an anomaly is any kind of data point that doesn't fit your data pattern. And the reason why you want to be able to spot anomalies is because if you have an anomaly, then you don't want to include it if you go to calculate a mean, which gives us our second point. That taking repeat readings allows us to calculate a mean or an average reading, which could make our results potentially more reliable, because we can kind of average out any kind of random errors. And again, the reason why then we want to spot anomalies is when we calculate the mean, we don't want to be including these anomalies, and these anomalies wouldn't actually be an accurate reading. Clearly, something's gone wrong there, and so it's important that if we take the repeat readings, we can actually spot these anomalies. Okay, figure 5 shows a graph of the student's results. I give 2 conclusions that could be made from the data in figure 5. So it's essentially saying what can we conclude from this graph. And so the easiest thing you can do here is essentially just explain the pattern that you're seeing, so the correlation. So we can see it's a positive correlation. So we could say that as the speed increases, what happens to the efficiency? Well, the efficiency also increases. So again, I'm just writing this shorthand. But it's 2 marks here, so we need a second point, and so that would be enough for 1 mark. So what would we get for our second mark? Well, you can see towards the end here what happens to our graph. It starts to level out. So compared to here, it's quite steep. So it's quite steep at the beginning, and then sort of starts to level out there. And so we can kind of explain this, that the graph seems to approach a maximum value or tends towards a constant value. Or in other words, the graph plateaus. Okay, so again, I'm just writing this shorthand. 5.4, give the main way that the motor is likely to waste energy. Well, the motor is a moving part, and with any moving part, the useful energy is going to be the kinetic energy, whereas the waste energy is usually, with moving parts, the waste energy is going to be heat. Okay, so the main way it's going to be wasted is heat energy. And where does that heat energy go? Well, it goes to the surroundings. So we're going to end up heating up the surroundings, which you don't really want, and that's a waste of energy. Question 5.5, when the total power input to the motor was 5 watts, the motor could not lift the 2.5 newtons in weight. State the efficiency of the motor. So for this question, we need to understand what is the formula for efficiency. Well, efficiency essentially is the total useful power out. So it's the useful power or energy out divided by the input power or energy. So in this case, we'll work with power since the power input is given to us. But we need to understand essentially what is the useful power. So in this case, the motor could not lift the 2.5 newtons weight at all. So in actuality, we didn't actually do anything useful because we didn't lift the motor at all. And so because of that, essentially the useful power out is going to be zero. The useful power out is going to be zero. Once the useful power out is going to be zero, well, it's zero divided by the input power. And the input power doesn't really matter what this is, because if you've got zero on the top, that means our efficiency is going to be 0%. Okay. Let's move on to question 6. Figure 6 shows a Van de Graaff generator that is used to investigate static electricity. Before it is switched on, the metal dome has no net charge. After it is switched on, the metal dome becomes positively charged. So it's explain how an uncharged object may become positively charged. Okay, so essentially it's a 3-mark answer, so we need to kind of give enough information in our answer for all 3 marks. And so we start off with our uncharged object. But actually, what we want to do with this uncharged object, we're going to explain how do things become charged. And so things become charged via the transfer of electrons. So that is something that you should be aware of. So how are we going to transfer electrons from our uncharged object to somewhere else? So essentially, in order to do that, we need something that's positively charged. So we bring a positively charged object, something that's already been positively charged. We bring that to our uncharged object. Okay, so what's going to happen when you bring that positively charged object to the uncharged object is you're going to end up transferring the electrons. So essentially, you've got negatively charged electrons, and they're going to be transferred to our positively charged object. Okay, so when you do that, you're essentially transferring away the negative charged from the neutral object to your positively charged object, and there you will leave a positively charged object. Okay. 6.2 then, figure 7 shows a plan view of the positively charged metal dome of a Van de Graaff generator. Draw the electric field pattern around the metal dome when it is isolated from its surroundings. Use arrows to show the direction of the electric field. So in this case, you should be able to understand the field pattern around a positively charged object. Essentially, you just have something like this. So you can draw a few different ones on, and essentially it's arrows which are pointing away from the dome. They're perpendicular to the surface of the sphere. So between the surface and the arrows, it should be a right angle. And you're going to have several of these. This is the classic field pattern that you're going to see when you have a positively charged object. As for the direction of the arrows, well, the direction of the arrows essentially show what would happen when you bring a positive charge into the field. And so if you have a positive charge next to another positive charge, it's going to be repelled away. That's why our arrows are pointing away from our object. Okay. 6.3 then, another positively charged object is placed in the electric field. Look at figure 8. In which position would the object experience the greatest force? And so for this question, you need to understand the relationship between the distance between the charged object and then the effective fields it feels from the field. And so what you need to understand is the closer it is to the source or the positive charge, the stronger the force is going to be. And so the closest one here you can see is going to be Q. And so we can take a Q. Okay, let's move on to question 7. A student set up the electrical circuit shown in figure 9. The ammeter displays a reading of 0.1 amps. Calculate the potential difference across the 45 ohm resistor. So here we're moving on to a circuits question. And all we need to do is calculate the potential difference across the 45 ohm resistor, which is this one here. And so essentially for this question, you can use our formula, V equals IR. So Ohm's law, V equals IR. So we should have the resistance. The resistance given to us is 45 ohms. And the current is also given to us of 0.1 amps. And so the current reading is taken from the ammeter here, but because it's a series circuit, the current is going to be constant throughout the series circuit. So we know that it's also going to be 0.1 amps flowing through the resistor here. So it's just 45 times 0.1, which gives you 4.5 volts. Okay, 7.2, calculate the resistance of the resistor labeled R. So this is this resistor here. And so for this question, essentially, again, it's going to be an application of Ohm's law, but we're going to try to understand this time what is the resistance. So we need to rearrange for resistance. So R equals V divided by I. And so what is the voltage that's flowing through our resistor here? Well, we need to understand that. First of all, what would the voltage be? Um, we don't know what the exact voltage that's going to be flowing through our resistor here. Haven't calculated it yet. So remember, in the case of a series circuit, the voltage is going to be split between the resistors. So we don't know what it would be right now. But what we can do is work out the total resistance of the whole circuit. So we know that the total voltage and the total current of the circuit is 12 volts and 0.1 amps. So the total resistance of the circuit is going to be given to us by just plugging those in. So 12 over 0.1 gives us a total resistance of 120 ohms. So that means that the total resistance of the circuit is 120 ohms, and we know within a series circuit, the way that you get your total resistance is you add up the individual resistances. So we've got three resistors here, 45 ohms, 60 ohms, and then our mystery resistance here, which we'll call R ohms, because the resistor is labeled R. So essentially 45 plus 60 plus R should give us 120. And so if you just rearrange that, it's quite a simple thing to rearrange. You should get that R equals 15. Yeah, R equals 15, or R equals 120 minus 45 minus 60, which should give you your 15 ohms. Okay, so in this case, what we had to do first of all was do this initial step here where we had to work out the total resistance of the whole circuit. And once we did that, we could simply use the fact that we know that the resistances in series add up to the total resistance. Okay, 7.3, state what happens to the total resistance of the circuit and the current through the circuit when the switch S is closed. And so the switch S is this one here. So essentially what's happening here is you have a parallel connection between this switch and this resistor. So what would happen is if you've got your current flowing through here, so let's just clean up this diagram a bit. So if you've got your current flowing through here, through your battery, it flows all the way here. And once it gets to this point, the current has two options. It can either go through the 60 ohm resistor, or it can go straight through here and avoid this resistor completely. And the current generally is going to take the path of least resistance. And the path of least resistance in this case will be the path with no resistor. So you can imagine this resistor essentially is going to be cut out of the circuit. And so essentially, if we answer the question, then what happens to the total resistance? Well, the total resistance we know is the sum of the resistances. So if one of the resistances is cut out, the sum of the resistances decrease, and so your total resistance decrease. So total resistance decreases. And then if you look at also the current, so what happens to the current? So again, we're looking at Ohm's law. So V equals IR. So we know essentially that if we have our voltage is going to be constant, the voltage hasn't changed, it's still 12 volts. But the total resistance within our circuit has changed, it's decreased. But we still need to be able to make up this 12 volts. And so if our resistance decreases, then our current is then going to increase to meet this 12 volts. So that's kind of the mathematical explanation. So as your resistance, if your voltage is constant, then as your resistance decreases, your current needs to increase. So the current through the circuit is going to increase. Okay, let's take a look at question 8. The student investigated how current varies with potential difference for two different lamps. The results are shown in figure 10. Complete the circuit diagram for the circuit that the student could have used to obtain the results shown in figure 10. So again, we've got another circuits question. For this question, essentially, we've got to look at what's going on. She's got two different lamps here. She's trying to see how the current varies with potential difference for the two lamps. Okay, and so essentially what we need is a circuit that's going to allow us to conduct this experiment. And the key feature of the experiment is that we're trying to look how the current varies with potential difference. So we're looking to change the potential difference, and we're trying to measure the current. So you need the key things you need to have is one way to change the potential difference and one way to measure the current in your circuit. Okay, so um, a, essentially, first of all, let's just draw it in our bulb. Okay, so we've got two lamps here, so we're going to put a lamp in there. You don't need to include both of the lamps. So the idea is you're going to do this experiment twice, and you're going to switch out the lamp A for lamp B on the second go. So you don't need to include both of the lamps. You then need a way to measure the current, and so we're going to put an ammeter, and remember ammeters are going to go in series. The next thing you need essentially is a way to measure the voltage. So again, look, we've got potential difference measurements on the x-axis. So we want to measure the voltage across the lamp. And so we've got to put these in parallel with the lamp. Okay, so the only thing we're missing here now is a way to actually change the potential difference that's going to our lamp. So we're looking to vary the potential difference and measure the effect that that has on the current. Now the way you do this is you have to remember in a series circuit, the potential difference is going to vary with depending on the resistance of your components. And so what you can do is you can put in here a variable resistor. Now the symbol for a variable resistor is a resistor with this arrow in here. And what a variable resistor does is it allows you to have a resistor here where you can turn a dial or do something to the resistor to change this resistance. So this resistor might have a range of 10 ohms to 100 ohms. And if you change the resistance of this variable resistor, what this means is that whatever voltage is coming out from your cell, so let's say 10 volts, it's going to be split across this resistor and your bulb and your lamp depending on the resistance of each one. So for example, if the lamp has a fixed resistance of, let's say, 100 ohms, so this is just to show you guys what I mean. If it's got a fixed resistance of 100 ohms and you set your variable resistor also to 100 ohms, then that means the resistance of both your components is the same, and your 10 volts is going to be split equally along those components. So you're going to get 5 volts here and 5 volts there. Then next you can decide, okay, you want to vary this variable resistor, so you're going to turn this down to, so just to make it easy, let's say you can turn this down to 0 ohms. So if you turn this down to 0 ohms, well, your resistance of your lamp doesn't change. You can't change that, but you've changed the resistance of the variable resistor. And so now all the voltage is going to be dropped across your lamp. So now instead of 5 volts, you're going to get 10 volts across here. And that way, essentially, you can change this resistance value to control the voltage dropped across your lamp. So that would be the kind of circuit that you'd have. Okay, 8.2, which lamp will be brighter at any potential difference, and explain your answer. Use figure 10 to explain your explanation, or to aid your explanation rather. So figure 10 is your graph here. So which one will be lighter? We can clearly see lamp A is consistently higher than lamp B for all potential differences. So that means the current at lamp A is always going to be higher for any potential difference at lamp B. Now, what does that mean that you're going to have a brighter bulb? Well, yes. Okay, so your first point is essentially it's going to be A. And why is it going to be A? Because A, you got a larger current for the same potential difference. So large current at any potential difference. And that means essentially that the power is going to be higher. So remember, the power is therefore going to be higher. So the power is equal to your current times by your voltage. Okay, and so if your voltage is the same, so let's say your voltage is 5 volts, and then your current is basically going to be the thing that makes a difference. So 5 volts times by 0.2 versus, or 5 volts times by this versus 5 volts times by a higher value, you're obviously going to get a higher power if the current is higher for the same voltage. And so therefore, if you've got a higher power output, then it's going to be brighter. Okay. Okay, 8.3. Lamp B has the higher resistance at any potential difference. Explain how figure 10 shows this. So for lamp B, you can see that the current is consistently lower for the same potential difference. So again, why does that matter? Well, essentially, think about your equation for resistance. So using Ohm's law again, V equals IR. We're going to rearrange this for resistance. So resistance equals V over I. And so as you can kind of tell, for a constant voltage, the higher the current, the smaller the resistance would be. And so you can see that for A has a higher current, then that means that the resistance is going to be lower. And so we can put this in simple terms then. So lamp B has a lower current. And again, this would be at any potential difference, lamp B has a lower current. And so that means that essentially, if you use the equation I equals V over I, then a lower current gives you a higher resistance. Okay. And so yeah, so it's just about, again, rearranging Ohm's law. Okay, question 8.4. Both lamps behave like ohmic conductors through a range of values of potential difference. Use figure 10 to determine the range for these lamps. So, and you also need to explain your answer. So, first of all, for this question, you need to understand what is Ohm's law. So, or sorry, what is an ohmic conductor? Well, an ohmic conductor is essentially the range of values. Well, an ohmic conductor is when the conductor obeys Ohm's law. Well, Ohm's law is V equals IR. And so if you plot a graph of current against voltage, what you should get is that your gradient will be equal to I over V. Your gradient will be equal to I over V, which is essentially equal to 1 over your resistance. And if your resistance is constant, then that means that this whole value will be constant, which means that your current over your voltage should be constant, and your current over your voltage is the same as your gradient, and so that means you should get a constant gradient. So a constant gradient essentially would look like a straight line. You wouldn't get a curve. So essentially we're looking at the portion of this graph for which lamp A and B have straight lines. And so it's quite easy to see. Essentially, let's look at lamp B first. For lamp B, up to about 3 volts, you've got a straight line. And for lamp A, instead, up to about 2 volts, you've got a straight line. So you can up to about 2 volts, you've got a straight line. And so you can kind of get a ruler and look at exactly what it is. And if you do that, then you should get you can see that it actually is about 2 volts here. So it's a bit difficult to see on this one, but you can see a slight curve over here. And so at this point, it's a non-ohmic conductor. But up to here, you've got 2 straight lines. And so you can say that the lamps are acting as ohmic conductors. So we go back to our question then. So the range of values would be 0 to 2 volts. So that's our first mark, just to identify the range of values. For an ohmic conductor, you should get a constant gradient. Constant gradient, or basically essentially a straight line. Straight line on the graph, as the resistance should be constant. Okay, so that would be your 3 points for your 3 marks there. Okay, let's move on to question 9. The student models the random nature of radioactive decay using 100 dice. He rolls the dice and rooms any that land with the number 6 facing upwards. He rolls the remaining dice again. The student repeats this process a number of times. Table 1 shows his results. Give 2 reasons why this is a good model for the random nature of radioactive decay. And so essentially we should have come across this example before of radioactive decay being completely random, and you can model this with a dice. So the reasons you can kind of say is essentially that for each of the die that you have, you can't predict which one is going to roll with the number 6 facing upwards. So you don't know which individual die is going to decay. So you can't predict individual die slash atom to decay. And so the second point is also you can't predict when it will decay. So if you select one of the dice at random, you select one of them, you can't predict on which roll it's going to decay. So you can't predict when. So it's kind of the same thing, but you can't predict when it's going to decay. Okay, let's move on to 9.2. So the students' results are shown in figure 11, and so this basically shows the number of dice remaining against the roll number. And use figure 11 to determine the half-life for these dice using this model, and show in figure 11 how you work out your answer. So you need to remember the definition of half-life. So half-life essentially is when half of the total atoms decay. So in this case, when half of the dice decay, how long does that take? So we can come across, we start off with 100, so if half of them decay, we'll have 50 left. So you go across to 50, and of course you want to use a ruler for this, go across to 50, and you just see how long that took. So it's about this number here, somewhere between 3 and 4. So that looks about 3.7 rolls. So if you did this with a ruler, you should get around 3.7. You can see it's just less than 3.8. And so we can put this in here as 3.7 rolls. Okay. So in this case, the half-life is kind of given in rolls. Obviously, normally it would be given in unit of time, like seconds or something like that, if you're working with actual atoms. So you get 1 mark for the answer and another mark to actually show you're working, and your working out on the graph should look something like that. Okay, should a teacher uses a protactinium generator to produce a sample of radioactive material that has a half-life of 70 seconds. In the first stage in the protactinium generator, uranium decays into thorium and alpha radiation is emitted. The decay can be presented by the equation shown in figure 12. Determine the atomic number of thorium-234. So this is a classic alpha decay equation, and essentially you need to be able to fill in the gaps here. And the way you could do this is, that an alpha particle has a mass number of 4 and a charge number or proton number of 2. So essentially, when you have the decay equation, everything on the right needs to add up to the left. And so we know that essentially this then is going to be 90. Because 90 plus the 2 will give us the 92 protons in the uranium that we started with. So the atomic number is 90. When protactinium decays, a new element is formed and radiation is emitted. The decay can be represented by the equation shown in figure 13. When protactinium decays, a new element X is formed. Use information from figure 12 and figure 13 to determine the name of element X. So for this question, you do need to be able to use your periodic table. And so essentially, we need to understand the type of radiation that's being emitted. So we say there's a new element formed and radiation is emitted. And so we need to understand what's going on. Well, what's happened here is we've gained a proton. So whenever you gain a proton, you should be able to identify what kind of radiation that is. And we can tell that this is a beta particle radiation. Now, in this case, this is not actually asking us what is the type of radiation yet. It's just asking what is a new element X. And so we've got all the information to be able to identify. You go in your periodic table and you need to look by atomic number. Okay, so by atomic number 92 should give you uranium. Now, the mass number may be different to what you see in your periodic table, and that will basically tell you that it's an isotope of uranium, but it's still uranium because it's got 92 protons. Okay, 9.5, determine the type of radiation emitted as protactinium decays into a new element. So this is where we come to this point here where we mentioned that this is beta decay. So with beta particle decay, what happens is you have a neutron in the nucleus of your starting element, decays into a proton plus an electron, and the electron is emitted as your beta particle. But essentially what happens then, that means is that you gain a proton, so your mass number increases by 1, but your total atomic mass, so your atomic number increases by 1, but your atomic mass stays the same. And the reason for that is essentially within your nucleus, all you've done is you've exchanged a neutron for a proton, and which both have the same mass. So for our answer, we can say that it's beta decay. So that would be worth 1 mark. And the reason why you can say that the proton number has gone up by 1, but the mass has stayed the same. And that should be enough to get your marks. You can also just write here that the neutron decays to a proton plus an electron. And your electron is going to be the thing that's emitted out as the beta particle. Okay, 9.6. The teacher wears polythene gloves as a safety precaution when handling radioactive materials. The polythene gloves do not stop the teacher's hands from being irradiated. Explain why the teacher wears polythene gloves. So essentially now we're looking at what is irradiation. So irradiation is basically whenever you have any substance brought into the presence of a radioactive material, it's going to be irradiated by that material. There will be some incident radiation upon it, but it itself doesn't become radioactive. And so essentially, that's exactly the point what we're making here, is that we don't want the radioactive material to transfer to the teacher's hands. So it prevents essentially radioactive material on teacher's hands. So essentially, what you need to understand is that even though the teacher's hands is being irradiated, that's not really the issue here. The issue is that we don't want to make sure that none of the actual radioactive particles themselves, or the non-radioactive mass itself, material itself, gets onto the teacher's hands, because if that happens, then you essentially have contamination of the teacher's hands, which is what you want to avoid, because that could cause damage. And you could have kind of outlined the kind of damage that would cause. So what kind of damage do you get from radiation? Well, it can cause things like cancer. Okay, let's move on to question 10. Electricity is generated in a nuclear power station. Fission is a process by which energy is released in the nuclear reactor. Figure 14 shows the first part of the nuclear fission reaction. Complete figure 14 to show how the fission process starts a chain reaction. Okay, so essentially here, we not only need to draw the fission process, but we also need to show how it starts the chain reaction. So for the fission process, the first step is always going to be that you produce your daughter nuclei, or your child nuclei. It's going to look like this, and you can label these as well as a nucleus. It's going to be your daughter nuclei, and perhaps more importantly, in terms of your chain reaction, you're also going to produce two neutrons. So I'm also going to just rearrange this diagram a little bit. So I'm going to put the two nucleus up here. So remember, essentially with fission, you're going to be splitting this nucleus into several different daughter nuclei, and that's kind of the key. But also on top of that, you're going to get at least one neutron. So we're going to draw two neutrons in here. I'm going to get a couple of neutrons being emitted as well. And the point is of a chain reaction that these neutrons can then go and react with another nucleus. Got a nucleus down here. And then again, you get this whole process going on where you've got the two daughter nucleus, or the children nuclei being produced, and you also get your neutrons being produced. So again, it was worth actually labeling all of these. This is a neutron, this is a neutron, that's a neutron, and that is a neutron. And for your 3 marks, that should be enough. Okay. Figure 15 shows the inside of a nuclear reactor in a nuclear power station. In a nuclear reactor, a chain reaction occurs which causes neutrons to be released. The control rod absorbs neutrons. The control rod can be moved up and down. Explain how the energy released by the chain reaction is affected by moving the control rods. So essentially, you need to explain when we lower the control rods, what actually happens. Okay, so essentially we start off with all our control rods up, and we have our chain reaction going on. Now when we lower the control rods, what happens is we start to absorb the neutrons. So we lower the control rods, and this absorbs the neutrons. So the control rods are made of a material that is able to absorb the neutrons, and if you imagine then you absorb the neutrons, you basically prevent the chain reaction, you basically stop the chain reaction. And as a result, what happens to the energy? So again, you need to look at the question carefully. It's asking us to explain how the energy released is affected by moving the control rod. So we need to directly say, how is the energy release affected? Well, when you stop the chain reaction, we decrease the energy being released. Okay, so hopefully that makes sense. Okay, 10.3. So figure 16 shows how the power output of the nuclear reactor would change if the control rods were removed. Calculate the rate of increase of power output at 10 minutes. So we're looking at the rate of increase. So the power is, again, you need to understand power is basically per second. So I think that is essentially giving us per second. But we want to calculate how fast our power increases. So essentially looking at per second. And so the way you're going to do this essentially is you will need to draw a gradient. So you want to be, so at 10 minutes, you've got a curve. Now, to calculate the gradient of a curve, you need to be able to draw a tangent. So you want to draw a tangent to this curve like this. Then you can draw on a little triangle, and essentially you can work out your difference in y and difference in x. You divide the difference of y by the difference in x, and that gives you your gradient. And if you go ahead and do all of that, you should get something between 240 and 276. So I'm just going to pick up 240, and it's giving you the units here. 240 megawatts per minute. Okay. Let's move on to question 11. So figure 17 shows a student before and after a bungee jump. The bungee cord has an unstretched length of 20 meters. And it's basically giving us this diagram here with all sorts of numbers put in for us. The mass of the student is 50 kilograms and the gravitational field strength is given as 9.8 newtons per kilogram. Write down the equation which links gravitational field strength, gravitational potential energy, height, and mass. And so this is one that you should be able to know off the top of your head. The GPE is equal to the mass times by the gravitational field strength. So I'm just going to write G, but you can write the whole thing out, times by the height. So you should write the whole thing out because it's giving you the whole thing in the question. Okay, calculate the change in gravitational potential energy from the position where the student jumps to the point 20 meters below. So the change is going to be essentially just using this formula. So the change in GPE be equal to the mass, which is 50 kilograms, times by the field strength, which is 9.8, times by the change in height, and the change in height is 20 meters. So you can see, sorry, the change in height is 55 meters rather. Okay, so the change in height is it was 20 meters. So it's given in the question. Sorry. The student jumps to the point 20 meters below, so that's 20. And so when you plug that into your calculator, you should get 9800 or 9800, and that is in joules. Okay. 11.3, 80% of this change in gravitational potential energy has been transferred to the student's kinetic energy store. How much has the student's kinetic energy store increased after falling 20 meters? And so essentially, 80% of the 9,800 joules that was transferred from gravitational energy have been transferred into kinetic energy. So we just do 0.8 times by that to find the total, which is going to be 7,840 joules when you put that into your calculator. Okay. 11.4, calculate the speed of the student after falling 20 meters. Give your answer to two significant figures. So for this one, you need to know this equation of the equation of kinetic energy. And so kinetic energy is equal to half times by the mass times by the velocity squared. So we can now just plug in all of our numbers. So the kinetic energy is 7,840 is equal to a half times by the mass, which is 50, times by v squared. And so when you rearrange for v, you should get 7,840 divided by 1/2 times by 50 on the bottom here, and all of that in the square root, and that should give you your total velocity, which is given as, when you round that off to your two significant figures, you should get 18 meters per second. Okay. Question 11.5. At the lowest point in the jump, the energy stored by the stretch bungee cord is 24.5 kilojoules. The bungee cord behaves like a spring. Calculate the spring constant of the bungee cord. Use the correct equation from the physics equation sheet. So again, we need to pick out the correct equation. And so the equation we're going to use is that the energy is equal to a half, times by k times by e squared. And so it's very similar to the equation we used above for kinetic energy, but the energy stored within a spring is going to be half times by the spring constant times by the extension. So the e is extension here. Okay, so now essentially we're just going to plug in our numbers. And so we know that the energy stored by our spring, which in this case is our stretch bungee cord, was 24.5 kilojoules. So you plug that in, 24.5 kilojoules. is equal to a half times by the spring constant times by the extension. Now to calculate the extension, we need to know that, we need to understand essentially what's the unstretched length and what was the length at that point, at the lowest point in the jump. So we need to go back above here. The unstretched length is given to us at the beginning of the question. It was 20 meters. And the bottom of the jump was 55 meters. And so the extension then would be 55 minus 20 equals 35 meters. You can see we've extended our bungee cord 35 meters. So everything up to here, 20 meters, would be unstretched. And once you get to this point, you then begin your extension, and that therefore at the bottom point you get an extension of 35 meters. We can go back to our question and plug this in. Half times k times 35, so 35 squared. And then when you rearrange, so your k should equal your 24,500. So you've got to convert this to kilojoules, convert that to joules, sorry, and divided by a half times by 35 squared. And when you plug that into your calculator, you should get a spring constant of 40. And so you end up with a spring constant of 40 newtons per meter. Okay, let's move on to question 12. A student wants to calculate the density of two objects shown in figure 18. Describe the methods that the student should use to calculate the densities of the two objects. And so here we're looking at how do we find the densities of objects. And so essentially there's two aspects to density, so we need to pull our equation. So a density, rho equals mass over volume. Okay, so we need first of all to find a way to measure the mass, and after we do that, then we need to find the volume, and after we know that, then we can just plug into our equation to find the density. So your first step then should always be that you're going to measure the mass. Now this is an experimental question, okay, so it says describe the method. So in these types of questions, you need to be very, very clear about what steps you need to take, and you need to detail every step that you're going to take. So we're not just going to say we're going to measure the mass. So we're going to use a balance. Using a mass balance, we're going to measure the mass. We're going to measure the mass of both of these. Now, for the metal cube, we want to find the volume, right? So to find the volume of the metal cube, it's quite easy to find the volume of a cube, right? The volume of a cube essentially is just you multiply the three lengths together. So the height times the width times by the depth. And so then volume of cube, you can find that by height times the width times the length. It's essentially just going to be the length squared. One length cube, sorry. So one of the length cubes, because it's a cube, all of these will be the same. So it's just the length cubed. And so essentially, if we want to find this length, then first of all, we need to actually find the length by measuring it. And how we're going to measure it, again, we need to be very clear every step, and we're going to do it using a ruler. So you need to make sure you write how you're going to measure the length. Okay, now to find the volume of the small statue is a bit harder. We don't have, it's not a simple shape like a cube where you can just multiply the length 3 times. So instead, for the small statue, we need another method. Now, a good method to measure volume when you have complex shapes like this is to use water. So for the statue, we're going to immerse it in water. So place the statue in water. And then essentially what you want to do is measure the volume of the water that's displaced. So the reason why this works is essentially if you imagine that you have a bucket of water here and you place your statue in, so I'm just going to draw just as a circle. So initially the volume of water, let's say, is up to here, so 10 centimeters. So you're going to have just this markings along the side. And then when you put your ball in, your ball floats at the top, and the water level rises by 5 to 15 centimeters. And so then if you know, if you imagine that this is straight, if we know the width and the depth, we can work out the volume of water that was displaced. So you can imagine this is going to be a 3D diagram. Hopefully that makes sense. And so if you know the volume of water that's displaced, that's going to be the same as the volume of the statue. So you write that in. And once you've got the volume of your cube, you've got the volume of your statue, and you've got the mass which you found at the beginning. And then when you want to use the equation of the density is equal to the mass over volume, and so you just plug that in to find your density. Okay, and so that should be enough. Question 13. An electrician is replacing an old electric shower with a new one. The inside of the old shower is shown in figure 19. If the electrician touches a live wire, he will receive an electric shock. Explain why. So here is worth 4 marks. So you need to make sure that you give enough information for 4 marks. And so essentially what we need to understand is, okay, so the live wire, what is the potential difference, or what is the potential of the live wire? So the potential of the live wire compared to ground is going to be 230 volts. So the live wire is at 230 volts. And so essentially then we also need to state why would there be an electric shock is because there's going to be a large potential difference between the live wire and the electrician himself. So for the electrician, the potential would be at 0 volts. So if the electrician is at 0 volts and the live wire is at 230 volts, once the electrician touches that live wire, there is going to be a current passing through his body. And the reason for that is there's a large potential difference between the electrician himself and the live wire. So here you can see there's a large potential difference. So you can see the difference in potentials, right? This one's 230 and the electrician at 0 volts. And so once he touches it, he's making a connection between an area of very high potential and a very, very low potential. And you've got a large potential difference, and that means you're going to get a large current flowing through his body, flowing through the electrician. And that is basically, that's going to be the thing that's responsible for giving him an electric shock. Okay. Different electrical wires need to have a cross-sectional area that is suitable for the power output. Figure 20 shows a recommended maximum power input to wires of different cross-sectional areas. The new electric shower has a power input of 13.8 kilowatts. Determine the minimum diameter of wire that should be used for the new shower. The diameter D can be calculated using the equation D equals the square root of 4A over pi, where A is the cross-sectional area of the wire. And so this essentially is just one way you're going to plug everything in. And so the diameter, so you need to work out the area. So when the power input is 13.8 kilowatts, so you go along to 13.8 kilowatts on your diagram, you come along here, you draw a line. Again, you'll use a ruler for this in your exam. And then you're going to go across and you're going to calculate the, sorry, it should be the other way around. So you go along here to 13.8 kilowatts on here. So you can use a ruler. I'm just doing this roughly. Go down, you find the cross-section area. It's going to be, in this case, about 9 millimeters squared. And then you can just plug it in. So it'd be 4 times by your 9 millimeters squared. So that's fine. Divided by pi and square root all of that. Now you can use the area in millimeters squared. You don't need to convert it. What you just need to be aware of is that the minimum diameter that you get is going to be also in millimeters. And so when you plug that in, and if you get the proper value from the graph using a ruler, then you should get a diameter of about 3.5. Okay. Question 13.3. The charge that throws through the new shower in 300 seconds is 18,000 degrees Celsius. The new question 13.3 then, the charge that flows through the new shower in 300 seconds is 18,000 coulombs. The new electric shower has a power of 13.8 kilowatts. Calculate the resistance of the heating element in the new shower. Write down any equations that you use. Okay, so for this question, we're looking at essentially, we need to work out the resistance of the heating element. Okay, so the first thing we've got a few different things here going on. We've got 300 seconds and we've got 18,000 coulombs. So we've got 18,000 coulombs flowing through our shower in 300 seconds. Now, you should know the relationship between coulombs and amps, or charge and current. So current, essentially, I, is equal to the charge, which we're going to write as C, divided by time. So the charge per unit time gives you the current, essentially. And so we can easily work out the current. So that's going to be our first step here. So the current is going to be equal to 18,000 divided by 300 seconds. And when you put that into your calculator, you should get 60. So you get a current of 60 amps flowing through our electric shower. And we know that the power of the electric shower was 13.8 kilowatts. And now we can come to our equation for power. Power equals the current times by the voltage. Power equals current times by voltage. And an alternative for this equation is power equals I squared times by the resistance. So the way we get this equation essentially is if we replace the voltage with V equals IR. So you take Ohm's law, the voltage equals V equals IR. Then essentially we can substitute V for IR. So, and then you get this equation here where power equals I squared times R. We'll just clean this up. Okay, so power equals I squared times R. And so now you can just plug in your numbers. So you've got 13.8 kilowatts over here. So you need to convert this to watts. So you're going to convert that to 30,800 watts is equal to I squared, which is 60 squared, times by the resistance. Then you want to rearrange for your resistance. So you get 13,800 divided by 60 squared. And that should give you a final answer of 3.83 ohms. Okay, so in this question, it's 5 marks, and the only thing you need to be careful of, essentially just go through it step by step. You can work out the current. You're going to need to write down the equations that you use. So you need to make sure you write down these two equations specifically, or these three, as you go along. And then essentially you're going to just go step by step, and you should get the answer of 3.83 ohms. Okay, so that's it for the specimen paper. Hopefully that made sense, and I'll see you in the next one.